thank you all for attending my defense talk. As you can see, my title is Frontiers of Full-Waveform Seismology. And during my 4 years PhD here at ETH, I had the pleasure to work on several frontiers in the field of seismology. And what I always found pretty fascinating about seismology, that it's quite useful. And on the other side, you can apply the principles of seismology across the scales. And during my PhD, I actually worked on different scales, and the projects that I'll be presenting are really moving from the global scale to the national scale down to the local scale. And also, seismology is pretty diverse in the things that you can look at. So to really break it down, seismology into 3 components. Most of the time, you have a seismic source that will emit a seismic wave field. This wave field will travel through a medium, and you will have measurements of said wave field. And during my PhD, I also contributed to all of these components. Let's first have a look at measurements. The measurements usually can look something like this here. This would be for teleseismic earthquake measurements. And you can already do pretty good and interesting science by just looking at a few phases, for example, the P wave or the S wave, or looking at the behavior of surface waves. But what I've always been interested during my PhD at was really to explore the full waveform, because there's so much more information in there that you can extract. So the principle of full waveform inversion and full waveforms in general are really to maximize the information per measured trace that we have, to learn more about the medium or the sources. Now I come to the medium, where I will quickly explain what tomography means. So this is to create a map of the subsurface in terms of wave speeds. And they can be really useful in many different applications. So for example, you can, in a dense urban area, you can have really highly resolved tomographic maps. And then you might be able to make a seismic risk assessment where you can tell that certain buildings might be more prone to the big, earthquakes that are coming in. Or on the other hand, you might be able to look at the structural integrity of a landslide with tomography. So how do you do this with full waveforms? Usually, you would start from the observations. Let's say we have the observations here, and then we create a numerical model and try to emulate the real world, which would look something like this here. And then we can solve the wave equation and perform, the numerical simulation, and see what at this receiver our forward would look like. And if we put them right on top of each other, we can see they don't really correspond to each other, like not to 100%. There's a slight offset. And the principle of full waveform inversion is to try to make this misfit disappear by updating our model. And how do we do this? Well, we basically look at this misfit, at the specific difference, and use this as a source in a second simulation that looks like this here. This is the so-called adjoint wave field. Please note that now the forward wave field, I will play this in reverse. And you can now see, when I run this, that the receivers now themselves have turned into sources with the adjoint source. And now how we can update the model is that we look at where the forward wave field and the adjoint wave field overlap, and this will then become our structural gradient. For only having like this one event and these 2 receivers, we don't really have a ton of information in there. As you can see here, we just see that we probably have to make it a bit faster. We now cheat a bit because this is just a synthetic setup. I know what the ground truth looks like. We actually want to image this blob here right in the center. And we can see that our data coverage is here not great for this. But what we can do is that we just add more receivers or also simulate more earthquakes. And at some point, we might be able to get something that at least resembles this blob in the center. But even now that we have tons of data, we still see that this gradient is not exactly the ground truth. So this really speaks to the fact that the problem is nonlinear, and usually you need many iterations where you update your model and just do the same thing again to then at some point converge and have a good waveform fit. All right, and then let's talk also about the sources. They have like source inversion itself, and seismic sources are quite interesting to look at for several applications. And some really important real-world applications are, for example, tsunami early warning. where if such a radiation pattern, as you can see here, might cause a tsunami, and this is important to know, or even for nuclear tests, to monitor nuclear tests around the globe, you might want to look for a radiation pattern that looks like an explosion. And how we do this with full waveform inversion is like this. So we go back to this slide here, and basically just have to look at the source location, or the presumed source location, and explore the adjoint wave field there. And when we do this, we actually get an idea what this radiation pattern looks like. And this also is a nonlinear problem that requires potentially a lot of iterations to converge. All right, and now I think we have all the ingredients to jump into my project. So like I said, we have these 3 components, but all of them are related to one method, which is full waveform inversion, that I will now apply first on the global scale for the medium. So global tomography is really our main source of information about the subsurface, because we cannot just drill deep into the mantle and look what it looks like down there. So we have to use these passive techniques to image the subsurface. And it's really for academic purposes. We might learn a lot about the mantle dynamics and the plate tectonic history and the entire evolution of our planet. Or it might also be useful to reduce the uncertainties in the source inversions that I presented before. The main challenges with global tomography are always that, they are computationally quite expensive, which is, to be fair, always true for waveform inversion methods. And specifically on the global scale, there's a fundamental imbalance in the data distribution. And my project tried to tackle both of these problems. But just to visualize how fundamental the imbalance is, let's say we take the earthquakes above magnitude 6. So we need some kind of threshold, because otherwise we don't have enough amplitude all around the globe to actually have a measurement. And let's just distribute these 2,500 earthquakes around the globe. And for a uniform distribution, it would look like this. But actually, our true distribution is really localized along tectonic plate boundaries. And I think if we look at the locations of seismic stations, this problem becomes even more severe. So let's say we have 30,000 global seismic stations. It would be pretty dense. But of course, we have oceans and land masses where we don't have too many data. So yeah, you can see that there's already a problem arising from this point of view. So if we want to perform a global tomography, this basically means that the resolution will always be held back by having to deal with the entire globe, with having this huge domain size. So it really makes sense to just focus on specific areas. So, and this would be the concept of regional tomographic models, that you look at, you're slicing up your data and just try to look at where you have enough sources and stations that you can actually say something about the subsurface. You can do this for several continents, or even on a smaller scale, also like here in the Western US or in the Andes. Yeah, and I'm not just throwing out random publications here. Actually, all of these publications have been combined within my project, within one global setup, which is the collaborative seismic Earth model, that combines around 20 of these models into one coherent model. So you can take these tomographic models, assemble them into one framework, but then you have the problem that you don't necessarily fit waveforms yet. So what you need to do is to perform a global full waveform inversion, starting from this model, where the idea is also, because we already have some information near the stations, that the deep mantle structure will be easier to resolve. And this is exactly what we've done on the supercomputer. We ran a global inversion for roughly 200 iterations, down to a minimum period of 50 seconds. And here you can see that we do indeed have waveform match. So what you need to compare here is in red the numerical model, and in black is the observations, and blue is just a comparable waveform if you had no 3D structure at all. So here for this global event, it works. And you should also note that the waveforms had to travel through several of these submodels. So this would imply that it has been correctly implemented. And now what's so special about the collaborative seismic Earth model is that you can zoom into a specific area, go down to a minimum period of, for example, 20 seconds in the Western US and still have a really good waveform fit. Right, and the end result you can see here. You can see that we have different resolved length scales. We can here see some subducting slabs. And really the CSIM is an evolving model because you can just simply add new regional tomographies to it and then maybe run a global inversion again. All right, and this concludes the first project that has been published. But overall, this problem that we have a very difficult data distribution is not exclusive to only the global scale. So seismologists have been trying to find other sources of seismic data. So for example, you might not be able to put down a dense seismometer network within a city or just on a volcano. It might be difficult. So over the past decade, what popped up is fiber optic sensing, where you can use a fiber optic cable and the laser signal that travels through it. And because the length of the cable changes with the deformations that come in from the seismic wave field, you actually do have a seismic measurement. And the most popular kind of fiber optic sensing is distributed acoustic sensing. So what you can see here is a earthquake measurement for a fiber that's like 12 kilometers long. You can still see here on the y-axis, this is the fiber direction, and this is the time, and you have a clear earthquake signal here. And what's so interesting about this is that you have really dense measurements of strain along the fiber. So you have to imagine that you now have like literally 1,000 of these individual waveforms that I've shown before right next to each other. So this is a really promising way of seeing the seismic wave field. I will talk a bit more about this in the later project. I just wanted to have it established that fiber optic cables are sensitive to earthquakes, where now we'll start with my second project, which really came out of nowhere in September 2022 with the Mulhouse earthquake. That was also widely felt here. If you were in Zurich at the time, you might have actually felt it. And right after this, we were approached by the Swiss Meteorological Service, by METAS, with a pretty unusual measurement, which was this here, which is clear as day a earthquake signal. However, METAS is not working with seismology whatsoever. What they're actually doing is that they're distributing the exact atomic time from the atomic clocks that are in Bern to a laboratory in Basel. And these atomic times are insanely precise, like 10 to the power of minus 17 seconds, which is just insane. And they somehow need to keep some of this precision when they ship this timestamps out to laboratories that are far away. The fiber optic link between Bern and Basel is 123 kilometers long. And any deformations that this fiber optic link is going through, you will lose precision. So what they came up with is something really smart, which is active phase noise cancellation. So they are actively just removing all of this noise that comes in. They can do this in real time to have a clean transmission of this time signal. So this, what you can see up here, is really for them not even a measurement, it's just noise. Usually they wouldn't even store this kind of information. And for us, it seems to be data. So my job in this project was trying to figure out how to simulate this with full waveforms. But first, we need to understand the physics, what's actually going on. And we can compare this with DAS quite easily, because this is not distributed acoustic sensing anymore. It's a different kind of fiber optic sensing called integrated fiber optic sensing, or short IFOS, which, if you compare it directly to DAS, is quite easy to visualize. So it's just integrating along the entire fiber. And now that we summed up along all of the lines here, we still have an earthquake signal, even though it's insanely compressed. So we only have a single time trace that we have remaining to analyze. So now when we perform a full waveform simulation for this setup, we have to consider the entire geometry. So we need to take off the wave field the adjoint, the strain field, and rotate it everywhere in line and sum them all up, one after the other. And yeah, we need to be really precise with the line geometry, because we can assume that this will have a massive impact on the measurements in the end. And then when you compare the observations to the synthetics, it looks like this here. So in black here, you have the bandpass filtered observations, and in red, the numerical model. And they do fit quite well. There's a bit of a shift, but overall, we were quite happy with this. So I would just like to mention that this PNC system itself was never intended for seismic measurements, and it still captures it. And we can actually understand these measurements with full waveforms. And I would even go as far as to claim that it's extremely difficult to use anything other than full waveforms for this type of measurement, because you have multiple phases arriving anywhere along the line at the same time. So it's really difficult to distinguish them. And also, potentially, you can have very long interrogation distances with this type of integrated fiber optic sensing, which makes this quite interesting. So these results have been published as well, but the story would not be complete to mention the work of a bachelor student that I supervised, who used only this measurement, only this data, to perform a source inversion with this data in a linearized manner. If we now compare here the radiation pattern that we have from the Swiss Seismological Service, and if you only had this data, your radiation pattern would look like this, which is pretty close to each other. This is within the uncertainty. So it seems that even though we only have a single trace, there's actually a lot of information in there that we can use. But this also made us think that we should probably have a toolbox to run full waveform methods for fiber optic sensing measurements, which now brings me to the final project that I'm going to be talking about today, where I had the goal to set up a toolbox where we can perform tomography or source inversions with the fiber optic full waveform data. And coming from seismometers and then moving to this type of data here, the main challenges are that we don't have displacements, but we have strain, so it's a slightly different physical unit. Then seismometers are usually point measurements, while fiber optic sensing data are averaged over a fiber segment, so you would need to take this into account. And of course, that the sensitivity of the fiber optic measurements heavily relies on the fiber orientation within the 3D medium. What I had to do for this is develop the adjoint method for this type of fiber optic data. I will spare you the equations. I will just show the final results here, where you can show that the correct adjoint source for this type of measurement needs to be inline-oriented moment tensor sources. You can see the radiation pattern here again. So if this now was a single dust channel, you have to discretize it in some way. And all of these moment tensor sources along the line share the same misfit that gets re-injected in the adjoint source. And now what I did is that I tested this entire code with a lot of synthetic inversions for source and medium. And because this was all synthetic, I had the freedom to decide what kind of setup I wanted to have. So I decided to go with Uetliberg. So you can see here, this is the Uetliberg Bahn. It's roughly 8 kilometers on the top to the Uetliberg summit here. And to test the source inversion, I just simulated an earthquake here. Then afterwards, I forgot about what model I used and just picked a starting model and ran the simulations again, compared the waveforms, and it looks like this. Then I started the inversion, the full waveform inversion for the source. And then you can correct the waveforms such that it's like this. And the model itself also wandered around in location quite a bit. here to the end. And if you compare this to the ground truth, it's pretty close. So at least for this here, it seems to be working. But interestingly, if we do the same with IFOS, take the same starting model, compare the initial waveforms to the observations, perform the inversion, we can still match the waveforms pretty well. And the source path that it takes and then comparison to the ground truth is also pretty close. There's some non-uniqueness here, but I find it pretty interesting that all the thousands of dust channels, if you have a good coverage, can, in theory at least, be ditched, and you can do the same with just a single integrated measurement. All right, let's move to tomography. For this, I collected 9 more observations. And because I had, again, the choice what I actually want to image, I chose a simple checkerboard pattern in 3D. For this here now, this is now back to DAS. For this setup, we get an image like this. And you can see that the checkerboard pattern agrees well, especially around the fiber. And what was not quite obvious to me, at least, was that we also have some depth resolution in this. So even though we only have horizontal strain measurements, or nearly horizontal strain measurements, we actually still have pretty good depth resolution here. Then we can repeat the same with IFOS. So keep in mind here, we only have a total of 10 seismic traces. The image that we get in the end is not quite as clearly resolved as the other one. So there's quite a lot of non-uniqueness going on. But interestingly, where we have a lot of curvature here towards the summit of Uetliberg, the checkerboard pattern seems to agree a bit better than anywhere else. So this package now exists for that we can perform full waveform inversion for DAS and IFOS. Also wrote a paper about it with the derivation of the adjoint sources and these synthetic tests. But ultimately, these synthetic tests are kind of boring. I mean, in a numerical world, everything seems to be working out anyway. So the real interesting part is when we go to real data applications. And this is what I think probably the most exciting aspect of my PhD. And it's really a shame that I'm not going to be talking about it a lot. But we had a lot of collaborations going on where my collaborators were working with PIBA already and trying to understand the full waveform measurements of DAS data. For example, Jonas was using it in Santorini on a submarine DAS cable that had earthquakes coming away from the volcano here in Colombo. Then Sarah is looking at a glaciated volcano in Iceland, is trying to do a source inversion there. Then we have Philippe working on a tomography on a landslide here in Switzerland. Tom is working on source inversions on the Gorner Glacier, also here in Switzerland. And Katinka was using it in the Bedretto lab to get the source radiation patterns of microseismic earthquakes. And all of this, I think if we want to put all of these projects into perspective, leads eventually to something which I would call global fiber optic seismology, where maybe at some point we can fill in all of these prominent data gaps in the oceans with the telecommunication cables that are available. At the moment, the problem, of course, still is that we don't have this data, and the internet providers are. Yeah, it seems to still take a while to actually get access to this kind of data. But at least the theory in all of this is already there. So we know how to use this data once it becomes available. Right. In the end, I would like to take a second to thank the SWP group. It's been really amazing working here, and it's been the greatest honor of my life to be here. Thanks to all of my collaborators. It was always a lot of fun. Also thanks to SPIN for funding me and having fun workshops. And of course, thank you to everyone in the audience today. Thanks.